guys, Mr. Cubby here, and this is about something called polar coordinates. So if you have that giant note packet, this is on page 37. Most of this is going to be from there. Some of it's just going to be some kind of random problems. So if you're looking at the PDF, this is like 37 page of it. But we're going to talk about polar coordinates, which are something that you normally learn about in MH, but you guys didn't because of how the spring went. And so right now, this video is not about calculus. This is just about polar coordinates. Okay? It's kind of like when we talked about parametrics as a system of graphing before we talked about how to do derivatives with it. That's kind of similar to what we're doing now. Okay? So I want you to think for a second about the idea of what a point, or how we like determine where a point is. So traditionally, if we are looking at a graph and you're trying to talk about where a point P is, okay, stick with me, I know this seems weird. You started with a point that you were trying to say like where P was relative to, in this case, the purple point. And the traditional way we've done it is we've then said, oh, I'll tell you where point P is by telling you how far over and how far up it is from the starting point, from our reference point. Okay? And the way we've always done that is by drawing a graph like this and calling that purple point the origin and saying it's over 4 units and it's up 6 units or whatever, and that's where the point P is. We've talked about how far over and up a point is compared to a starting point. Polar coordinates idea is a completely different way to describe where that point P is relative to that starting point, that starting purple point. Instead of talking about how far over and up it is, we think about that point P and we think about how far away it is from the point P. Makes sense, right? Oh, just tell me how far away it is. And we think about at what angle it's at compared to like right here. So we think about like, hey, that point P is at a 30-degree angle and it's 5 units away from that starting purple point. And those two pieces of information, so instead of telling you how far over and how far up it is, telling you how far from the starting point it is and at what angle to go at, that's enough information to describe any point. Okay? If you don't believe me, just try it. Like if you want to know where this point was, well, just figure out how far it is from our starting point and figure out what angle to go at. And if you have those two pieces of information, you could say where that point was. Those two pieces of information are how far it is from the starting point and at what angle you need to draw at. So going back to our notes here. We call those two things r and theta. R is the distance from that starting point, and theta is the angle, starting with the positive x-axis, to go to draw that point. Okay. We call that starting point the pole. Instead of calling it the pole, we started calling it the origin, we call it the pole. So if you want to plot the point 230 degrees, that point P is 2 units. So here's our pole, there's our origin, we call it the pole now, in polar coordinates. And that point P is 2 units from the pole, and it's spun up at a 30-degree angle. That's where it is. That point Q is 1 unit from the pole, and it's spun 3 pi-4 radians from the positive x-axis. And that tells you where the point is. Again, we're abandoning the idea of over and up, and instead doing how far from the pole and at what angle. Okay. When you actually plot a polar point, read this point really quick. So even though they tell you the r first and the theta second, it's actually easier to think about the angle and then go out that far. So plot point A, for instance, it's easier to think, oh, go at a pi-6 angle, and go out 2 units, here would be point A. Okay. Go ahead and plot all those points real quick. That's where you should get those points. You might have noticed that D had a negative R. Well, how do you deal with that? Not a big deal. You just go to pi fourths, but instead of going out 3 units that direction, you go out 3 units the other direction. So when you have a negative R, you instead of going out, you go like backwards through the pole and go out the other direction. Okay? What do you do if you have a negative angle? Well, you just rotate backwards. That's normal. And so negative or 3 negative pi halves, you go negative pi halves and then go out 3. It's easier if you plot the theta first and then think about how far from the pole. What happened with E and F? They're at the same place. So because of coterminal angles and that negative R business, you can have 2 points that look different but actually plot to the same place. Going at an angle of negative pi thirds and going out 2 is the same as going at an angle of 5 pi thirds and going out 2. There's actually infinitely many ways to name any place because you can have coterminal angles. Okay. So that's just a weird thing that can kind of happen. Okay, and we can go through this really quickly. I'm not gonna, this is not the focus here, but hey, so if you have a point 3, 7 pi 6, there's a few different ways to also name that. You could say, oh, you mean 3 negative 5 pi 6. Or how about this? Instead of going to 7 pi 6 and out 3, you could just go to pi 6 and go out negative 3. Because if you did that, then you'd go, starting at your pole, you go out to pi 6, but then you go backwards that direction. Or you could go out 3 and you could go out to 20 pi 6. Excuse me, 20, yeah, 20 pi 6. 10 pi thirds. Okay. Cool. Not the focus though. One other thing, there is a way to switch back and forth between polar coordinates and regular coordinates. Remember, regular coordinates are called rectangular coordinates or Cartesian coordinates. There's a way to flip back and forth, and you can get a way to do that based on just thinking about this geometrically and getting a bunch of connections between x's and y's and r's and thetas. It's something that you spend a lot of time on in MAH. It's not something you really need to know for BC, but I feel like it's worth throwing out real quick. So if you look at this picture, we can fill out a bunch of stuff. Look, we have our angle theta, our radius r. That's why r is called r, because it's like a radius. And you simultaneously think about this point as being over x and up y. You look at this picture, the cosine of that angle is x over r. The sine is y over r. So x equals r cosine theta, just doing a little rearranging, and y equals r sine theta. And r squared, we could do Pythagorean theorem, x squared plus y squared would equal r squared, and the tangent of theta would equal y over x. These relationships let you take thetas and get x's and y's, or take y and r and get, or excuse me, take r and theta and get y. So they let you flip back and forth between xy and r theta. And that's not really going to be our focus at all. We really don't need to know that, but it's something that's kind of cool at least. Let's do one of these really quick. Here's a polar point. There's our r. There's our theta. We want to figure out the angular coordinates. Okay. Well, if we know r and theta, we can figure out x and y using this information right here. Okay. So since r is 6 and theta is 2 pi thirds, x will be 6 times the cosine of 2 pi thirds. Y would be 6 times the sine of 2 pi thirds. Cosine of 2 pi thirds is negative a half. So x would be negative 3. Sine of 2 pi thirds is root 3 over 2. So the y would be 3 root 3. So the point, the rectangular point, negative 3, 3 root 3. That xy is the same as r is 6, theta is 2 pi thirds. So plotting that point, This point rectangular is the same as this point in polar coordinates. Okay. Okay. Again, just something you spend more time on in MAH, but not terribly important for our purposes. Okay, let's talk about some stuff that you do kind of need to know how to do. First, how would you actually just graph a polar function? Well, if you don't know what it looks like, you know how you just plug in x's and y. You plug in x's, you can get out y's to graph a regular rectangular function. Well, if you have a polar functions are written r in terms of theta. Well, how do you graph it? You make a table, you plug in thetas, and you get out r's. Okay, so you just plug in some thetas. Again, theta is an angle, so what should we plug in? I don't know, 0, whatever you want, pi fourths, pi halves, 3 pi fourths, pi. Let's just do that to start. Plug it in, figure out what r is. Okay. These are the points I got. If I was then going to go plot these, I could plot them. Remember to think about the theta first. So if I went to an angle of 0 radians, I'd go out 3. That would be 1 point. And I go to an angle of pi fourths, I'd go out 3 root 2 over 2. 1.5 times root 2. Root 2 is like 1.4. 1.5 times 1.4 is 2-ish. Yeah, okay. So I go to pi fourths and I go out roughly 2. I go to angle pi halves and I go out 0. I go to an angle of 3 pi fourths, going at this angle, and I go out like negative 3 root 2 over 2. Okay, so I go this direction, right about that much. Then if I went to an angle of pi, I went shot out at an angle of pi. How far out would I go? Ooh, negative 3, so I go back over here, back where I started. Those are 4 points I got. You could get some more points if you wanted to. What does the shape end up being? It doesn't end up being a diamond. It actually ends up being a circle. You get a couple more points. Makes that clear. So r equals 3 cosine of theta is a polar circle. How do you do this on your graphing calculator? That's easy, and we're going to do this a lot. Grab your graphing calculator, follow along with me. First thing you need to do is switch the mode, okay? So you click the mode button, and we're in normal function mode. We need to go over to POL, polar mode, okay? So then when you go to y equals, it's r equals now. What do we want r to equal? 3 cosine theta, okay? Like with parametrics, polar graphs repeat themselves a lot, and we'll see that. But I graph this, and oh, I get that circle. It's a little sloppy there. You can change, we'll talk about that later. Yeah, well, we'll talk about it now. You can change what thetas you use. So like maybe you want theta to go from 0 to pi or something like that. Keep in mind that theta is an angle, so we usually have stuff involving pi's. And then you can also change what x's you see. Like if you don't want to see that many x's, we can just go x from -5 to 5 and y from -5 to 5. You get a normal graph window stuff, okay? We get an idea of what that polar graph looks like, and it graphs it for us. Cool. Read this really quick. This is nice. So we're really not going to do this table thing, but they're either going to give us the picture or they're going to let us use our graphing calculator to graph it. Cool. Okay. A common question that they ask about polar functions that we'll need to know for various things is, hey, when does the polar function go through the pole? So a lot of these polar graphs loop around, and sometimes they crisscross on themselves and stuff. But the question about when does it go through the pole, remember the pole is the origin. So this graph whoops around, and they want to know, hey, when does it crisscross through the origin? When does it go through the pole? And if you think about what going through the pole means, and they're asking you when that happens, they're asking you for the theta that happens at. And when you go through the pole, that means your r is 0, right? You're 0 away from the pole. So how do you figure out when a polar function goes through the pole? You set the radius equal to 0. Yeah, so when does something go through the pole? When the radius equals 0. How do you solve that equation? Well, this equation we can actually solve by hand. Solve that by hand. Pause and solve that trig equation by hand. Okay. So if you actually graphed this, what happens with this guy is when theta is 0, you're right here, and then you go brrr. When theta is pi thirds, it goes through the pole, smashes through the origin. Keep going, theta gets bigger and bigger and bigger, you keep going around, you keep applying points, blah, 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 and then at 5 pi thirds, it smashes through the pole again. So if you're talking about between 0 and 2 pi, there's 2 theta values where this function goes through the pole. Again, you figure out where a polar function goes through the pole by setting r equals 0. Okay. Let's look at a similar problem. When does this polar function go through the pole? Okay. A lot of polar functions are like swirls and circular things because of that whole theta angle idea. You know, you're like going around. A lot of times they're like swoops and curls and stuff like that. Okay, when does this guy go through the pole? I'm going to set r equal to 0. Okay, 2 cosine of theta equals 2 theta. I can divide both sides by 2. When does cosine of theta equal theta? I don't know how to solve that algebraically. That's because you can't solve that algebraically. Okay, so we're hitting a situation here where I don't know how to solve this algebraically. So I'm going to need my graphing calculator. Grab your graphing calculator. Type this in. Graph it, please. Okay, so I typed in my graphing calculator, 2 theta minus 2 cosine theta. I graphed it. I got this. I'm trying to figure out when it goes through the pole. Okay. Remember, everything good in your graphing calculator, when you're looking at the graph, is always in second calc. This is where all the stuff is. So I'm going to go there, but there's a thing there. Huh. What you'll see here is there's only 3 things that you can calculate on a polar graph. Value. Well, that just asks me the theta. Like I can type in a theta like pi, and it will tell me out the r. Okay. That's not going to help me figure out when it goes to the pole unless I like guess and check or something. The other 2 things are dy dx and dr d theta. What are those? Oh, those are derivative stuff. Okay? So we'll talk about those when we talk about derivatives of polar functions. But your calculator can do polar derivatives, and that's what those 2 things do. But back to the question at hand, it can't help us figure out when this polar goes through the pole. Okay? And what you actually need to do is you need to look at this function, excuse me, this equation, and say, this is the equation I want to solve, right? It comes from this polar function and me wanting to figure out when it goes through the pole, and so I set r equals 0. But I just want to solve this equation. Once you figure out the equation that you want to solve, it has nothing to do with polar. This is just an equation you want to solve. You actually do not want to be in polar mode. Because if you put it in polar mode, there's nothing you can do to calculate when it equals 0. Like that just doesn't happen. It's just not something your calculator can do. So what you actually want to do is solve this equation on your calculator. A lot of you guys seem like you're sketchy about how you solve an equation on your calculator. This is how you solve an equation on your calculator. You put the one side in, y equals, you put the other side in, y equals, and you figure out where they intersect. Okay? We're doing this in rectangular mode. That's how you solve an equation in your calculator, in rectangular mode. You go to function, you go to y equals, the one function is just 0, which is just our x-axis. The other one is 2x minus 2 cosine x. And I want to figure out when those 2 things equal to each other. Specifically, I'm looking for an x value of theta between 0 and 2 pi, so I can change my window real quick to 0 to 2 pi. I'm only looking for solutions between 0 and 2 pi. I can graph it. When does this 2x minus 2 cosine x equal 0? I know, you don't need to type in thetas. You can type in x's. We're just solving an equation. When do those equal each other? Right there. That's when it equals the x-axis. How do you find that point? You go second calc. Usually I do intersect, or I could do 0 here since it happens to be an x-intercept, but I'll do intersect since I typed in the first curve. X equals 0.739. Okay, that's telling me that the value that solves that equation is 0.739. I solved that equation in rectangular mode, but it's telling me something about this polar function. Okay. Solve that in rectangular mode. Okay, one more thing here. Let's say you got two polar graphs. I got r equals 3 cosine of theta, that first one we looked at, which is this red circle. And I got r equals 1/3 theta, which is this purple little swirl. I'll draw them better. And clearly those two things intersect. Okay, and I want to figure out where they intersect. Okay? But I don't do that in polar mode. Okay, if I tried to graph these two things in polar mode of my calculator, I get an idea of what the graphs look like. If I actually want to figure out where they intersect, my calculator in polar mode can't help me. I want to figure out for what theta value these two things equal each other. This is just an equation I'm trying to solve. I can't do it algebraically. I hope you recognize that that's not something you can solve algebraically. There's no algebra that exists that I know that you can use to solve that. So we're going to solve it on our calculator. We're going to do it in rectangular mode. You solve equations on your calculator in rectangular mode. It doesn't matter if those equations came from a polar function. So when these two things intersect, I set them equal to each other. It's something I cannot solve algebraically, so I solve it on my calculator, but I solve it on my calculator in rectangular mode. That's how you solve equations on your calculator. Go to your calculator, solve that equation. Unpause and I'll show you the answer in a second. Go to your calculator and actually solve that. Okay, I went to my calculator. I typed 3 cosine x in y1. I typed in 1/3 x in y2. I graphed them both. I figured out where they intersected. I did second calc intersect. Oops, it went away. I'll do it again. I did second calc intersect. Remember how this works? You just try to go close to the point of intersection and you just hit enter a few times. Okay? And it tells you the x where they intersect. In this case, in this problem, it's actually a theta. Theta equals 1.413. It's the theta where those two polar functions intersect. It's asking me to find the polar coordinate, the full coordinate, r theta. I only found the theta. How do I find the r? Well, if I know the r, excuse me, I only found the theta. I want to know the r. I can just plug the theta in to figure out the r. Okay, so I just plugged it in, that theta, into here to figure out the r. And I can check if that makes sense. Okay, here's my r, here's my theta. If I go out at an angle of 1.43 radians, that's almost pi halves radians, and I go out 0.4, yep, that's right where they intersect. Okay, cool. I hope that gives you a little bit of an idea of what this whole idea of polar coordinates and polar functions are in terms of theta. And what we're going to do is some calculus with polar functions. That's the next thing we're going to do. Starting out with some derivatives. All right, thanks for watching.